So the next talk is about HEaaN.MLIR, an optimizing compiler for fast ring-based homomorphic encryption, which will be given by Juneyoung Lee.
Hello, my name is Juneyoung Lee, and I'm working for AWS right now. And this work was done when I was working for Crypto Lab in the past. First of all, let me briefly introduce what homomorphic encryption is. Let's assume that there is a function f that turns this black paper into this blue paper. In homomorphic encryption, what we want to do is to find the three functions, encrypt, large F, and decrypt, that first turns the black paper into a secure black paper and somehow turn it into an encrypted, black paper, and turn it into a secure blue paper, and finally, if you decrypt it, then finally becomes the blue one. Then when is it useful? It is useful when our device has limited computational power and limited storage, and we want to somehow leverage the power of the large clouds such as AWS and other things. And we call this a secure cloud computing. Then, ideally, we will be able to avoid the privacy issues in ChatGPT, allowing us to use the ChatGPT in companies. And then the question is whether this is a realistic plan. And it is hard to say whether it is indeed realistic at the moment, but it is continuously improving. So in this HEaaN.MLIR, there is an image classification training that was done by homomorphic encryption within 1 hour and showed some nice accuracy. Then, how can we design these three functions? It consists of 2 steps. The first one is choose the encryption scheme that we'd like to use and determine its parameter. Here, there are a few encryption schemes that are known in the world, and each encryption scheme determines available unit operations of having some characteristics. And for each encryption scheme, we can give some parameter that determines security level and the size of ciphertext and etc. In step 2, we write the encrypt and decrypt and also the large F function using unit operations. Then let's dive into the example. Let's assume that we'd like to implement a homomorphic encryption version of summation, which takes an array of having 10 elements and calculating the summation of each element. First, we need to choose some encryption scheme. Let's assume that we choose a scheme that is called CKKS. CKKS provides seamed unit operations on the ciphertext, and this includes addition of elements and cyclic shift of elements of the array, and also encrypt and decrypt. And then we can also determine the parameter of the ciphertext, such as the number of slots in the ciphertext, which should be not less than 10, because we are dealing with an array having 10 elements. Then we write the three functions using these unit operations. First of all, encrypt can be simply implemented using the encrypt unit operation in CKKS. Second, to implement the large F, we can use the addition and cyclic shift of the array by shifting the elements of array one by one and adding the shifted arrays. And then the decryption is defined as decrypting the added summation of ciphertext and returning any elements, because all elements should be homogeneous. Okay, so it seems kind of simple, but there is a real challenge, which is that unit operations are typically kind of slow, so we need to make them fast. But it is hard to make them fast, and there are 2 problems. The first one is that the homomorphic encryption is supposed to run on kind of diverse running environments. First of all, if it is run on-premise, then we can use the data of our party without encryption, because we don't need to encrypt the data of ourselves. Also, there are clouds that conveying the ARM chips, such as Amazon Graviton 2 and 3, and we can use GPU, but since homomorphic encryption uses a lot of integer arithmetic, this wastes a lot of transistors for the floating points in GPU, so it is not cost efficient. The second challenge is that there are many unit operations and they keep growing. So it'll be great if we can deal with that. In order to resolve this solution, in order to resolve this problem, the existing solution is to define a high-performance numeric library that can be used for homomorphic encryption, especially for some encryption schemes that are called ring-based homomorphic encryption. The unit operation contains a lot of polynomial ring operations. This polynomial ring seems scary, but in high level, they are just kinds of polynomials whose degrees are not larger than 10, and their coefficients are less than q. So to compare this to deep learning, in deep learning, matrix operation is the most effective, most computation-intensive one. Then in ring-based homomorphic encryption, the polynomial operations are indeed the cost-expensive one. And in order to resolve this issue, we have Intel Hexel that supports AVX512 in order to accelerate these polynomial operations. Then what is the limitation of this problem? There are two issues. The first one is that it is hard to fuse these individually accelerated polynomial operations. For example, let's assume that we have this one addition and one subtraction. Then we'd like to optimize this code by making a one large loop that does the addition and subtraction of the coefficient inside this loop body. But since polynomial operations are individually accelerated, fusing these two loops becomes hard. The second issue is about optimizing integer modulo operations. If the result of some polynomial is only, or integer, is only used by function that satisfies this property, which is fx modulo q equals fx, then we can remove the percentage. And in order to do this optimization, we need to do some analysis on the program. So we proposed the HEaaN.MLIR, which is the MLIR compiler framework-based the compiler for fast unit operations. It takes MLIR source, which takes two intermediate languages of compiler, which can be defined inside the MLIR framework, which are called poly and mod aris. Poly is an intermediate language for polynomial ring operations, and mod aris is a slightly lower level operation that has modular arithmetic on integer tensors. Then HEaaN.MLIR first does optimizations on this program by doing cross-polynomial operations, and then lowered it into the integer tensor program, which can be readily dealt with the MLIR framework. So by incorporating the compiler optimizations that I've introduced before and running those, we could observe that there was a significant speedup compared to the highly optimized proprietary libraries such as HEaaN or open source libraries such as Microsoft Seal. Okay, then let me briefly introduce how we can write the unit operations in this poly intermediate language. In order to show this, I will briefly introduce how the encryption is done in the CKK scheme. It looks complicated, but it is pretty simple. Encrypt takes a polynomial and returns a pair of polynomial. The first value of the pair is m minus a dot s plus e, where s is the secret key and a and e are some random polynomials. And the second element of the result of encrypt is the random value, which is a. Before introducing how this can be represented in poly, I'm going to introduce two interesting facts about this formula. The first one is that the polynomials are represented as two-dimensional integer arrays, unlike one-dimensional integer array, because we might imagine that it should be one-dimensional array because it only has a list of coefficients, right? But in practice, there are two-dimensional arrays because the modulus q is actually represented as a product of k small primes. So we have two-dimensional arrays which has the modulus for each small prime. The second fact is that the polynomial multiplication is expensive, and in order to deal with this, we need to somehow have an alternative form of polynomials. And I'm going to call this entity form in this talk for brevity. But yeah, so there is an entity form and there is the ordinary form. And these two forms can be interchanged. So we need to implement this in our language. So this is the program that is written in Poly that describes the encryption. First of all, we have this attribute which describes the homomorphic encryption parameter, which is called ckks.fba. And then the function takes two arguments, which is the plain text and the secret key, called m and s, and returns a pair of polynomials as described before. You can see that each type is called poly entity with the bracket having some name called ENC max. And this ENC max describes the number of small small primes that I've described before. And then we can first do the random sampling that is necessary to do encryption and do the multiplication and subtraction and addition. Like this, we can implement the unit operation of homomorphic encryption using the Poly language. But sometimes the Poly language isn't expressive enough. In this case, we can use the mode RS intermediate representative language that is not described in this talk. And furthermore, we can also utilize the generic MLIR operations. HEaaN.MLIR has three optimizations that are important for the performance of homomorphic encryption. The first one is optimizing Barrett reduction, which is an integer modular operation that is optimized when the modulus q is fixed. The Barrett reduction consists of two steps. The first one is approximating x modulo q, which can be either the true value x modulo q or x modulo q plus q. And then, in the second step, we can finally calculate the accurate answer by subtracting q if it is not less than q. And the interesting fact is that we can omit the step 2 if the value t does not need to be exact. And in order to determine whether the t needs to be super precise or the approximative form is enough, we do two kinds of analysis. The first one is traversing on a data flow graph and annotating modulus policy, which defines how accurate the result of modulus should be for this operation. And for the second approach, we record a list of specific patterns of interest that can be further optimized, which cannot be handled with this the first general analysis. The second optimization is loop fusing. In the case of homomorphic encryption, there are two cases where loop fusing can be done. The first one is simple pointwise loop fusion, and the second one is fusing the outer loop only of nested loops, because the outer loop typically iterate over the small prime numbers that makes the modulus. And the third optimization is auto-vectorization of loops. And this is important because the homomorphic encryption code typically contains a lot of 64-bit multiplication, especially multiplication high operations. In order to do this, we use profiling approach. For each loop, we try to optimize the loop using some policy, and then we estimate the measure the performance of the loop after applying the optimization. Then we can build a profile that is basically a two-dimensional table that describes for each loop what is the performance after applying this optimization. Then finally, by combining the result, we can finally make the optimal choice. And this is the evaluation. In order to evaluate the performance of HEaaN.MLIR, I chose two competitors for each scheme. I precisely re-implemented the algorithm they used, and then compared the performance on the three machines. On the single core machine, we could see around 20 to 30% speed up in average, and also for maximum about 200% speed up. And also for multi-core speed up, we could see the similar result. Also, we could implement a 3-layer neural network for a competition that is called I-, and we could see 60% speed up. Okay, I'm going to has the detailed graph. And this is the conclusion. We proposed a compiler, HEaaN.MLIR, for fast unit operations on ring-based HE. Okay. Yeah, and it worked well, and it shows some speed up. Thank you.
Thank you. Thank you for the speakers. And so, questions? Do you have any questions? Yeah. 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 No problem.
Hello, thank you so much for your talk. I very much appreciated the intro to homomorphic encryption. My question is about the profiling part you just mentioned in the last slide. Is that portable? How much do you pay for profiling for getting that two-dimensional LJ table?
Yeah, that is a very good question. I remember that it typically took around 10 times more than the actual evaluation, because there are many portfolios that we'd like to try. So, yeah, I think the scale factor is around 10.
Yes, but then the question is, you have a very nice algorithm, but it requires something that is prohibitive to obtain in order to be so competitive as you showed in your results. So would it be possible maybe to use dynamic scheduling of these loops that don't need profiling?
Yeah, that is a good question, good suggestion. And yeah, I haven't thought about the direction. Thank you.
No problem. We can talk offline if you want.
Yeah.
Thank you.
First off, great talk. A couple of specific questions about both the fusion and the vectorization. I'm curious how much of this is done specific and or requires any specific information for FHE, and or how much of this is more generalizable, either in existing MLIR or could be used elsewhere. And sort of a follow-up to that, did you compare with, say, a polyhedral optimizer in MLIR or the likes?
Okay, for the last question, yeah, indeed there were compiler developers who suggested trying existing polyhedral optimizations, and well, I thought that it would be a good idea, and indeed it will bring better performance. But I kind of thought that the loop shapes are somewhat canonical. So what I mean is that many loop looks pretty the same in the homomorphic encryption after the polynomial operations are lowered into the loops. So I thought that if I can implement optimizations that are tailored for that, then probably the performance would be somewhat similar to the existing polynomial optimizers. Yeah, so that is my answer. And what was the first question? Sorry.
Yeah, I guess how much domain information from FHE is required for any of these transformations, or are these sort of more generalizable?
Yeah, that is a good question. Yeah, for example, I needed to implement matrix multiplication for this compiler, and well, there are and writing fast matrix multiplication is a well-known problem, right? But in the case of homomorphic encryption, the matrices are not very regular. They look really thin. So yeah, you know what I mean. Yeah. So the general matrix multiplication algorithm, fast algorithm could not be applied, and I needed to somehow use a customized one. So yeah, to summarize, I think we need some knowledge in SHE in order to write the optimization that are tailored for HE. Yes.
Makes sense.
Yeah. So quick question, please. Yeah.
Hi, thank you. This is a very interesting talk. So first of all, I guess, would I be correct in assuming that the way that you get speedups over these like other libraries like SEAL is the fact that you can optimize across operations instead of just within each operation? And then I guess as a follow-on to that, to what extent do you do any kind of like scheduling of your operations to like maximize the like the loop fusions that you get from like 2 multiplies or something like that?
Yeah, that is also a good question. So in the tensor form, if we represent the program in the tensor dialect or tensor intermediate language that is provided by MLIR, each tensor is a value. So each polynomial operation has no side effect. Therefore, we can the scheduling of the operation isn't very critical in doing the optimization. But one problem was that MLIR isn't good at describing some operations like number theoretic transformation, which we briefly mentioned in this talk. And in order to deal with this, I need to somehow tweak the MLIR. And in this case, the tensor could not be represented as the SSA form anymore. So in this case, the scheduling really mattered.
Okay. Okay. Thanks. Thanks for the speakers. And can you quickly switch? Yeah, that was